mentorship and taking courses as high school students, because I love that kind of stuff. But if you have those questions, we'll save them till later. Okay, so going backwards, we saw that we can take a reflection and we can write a formula for it, right? We can write this kind of matrix that says where things go. So now we can do algebra with symmetries. We can represent symmetries algebraically. And now that you've got your paper, I would like you to try and write down a matrix that represents that rotation. Okay, that 120-degree clockwise rotation. So try and write down a formula for it. Right. So, just like here, we wrote down one of these things that says 1 goes to 1. Just like we wrote down that.
Write the matrix for that. I want us to write a matrix for that.
I want you to write one of those things for the rotation. So write down a brackets and
rotation, okay.
Yeah, but for the rotation now. Yeah, so 120-degree rotation clockwise. Did it? Yes!
How many degrees is this again? Sorry?
120. 120 clockwise. Looks great. Perfect. Okay. All right. Who's got a formula? Who's got a formula? Hands up. Hands up. All right. Matrix formula thingamajig. Okay. All right. Is it that one? Yeah. Yeah?
No.
Yeah. Works.
No.
Okay. Oh no.
I did the opposite.
It's the opposite.
Yeah.
Aha.
I
It's
did 2, 3, 1.
Did you do it counterclockwise?
Oh wait, I did it that way. Okay.
That's fine. That's good. Okay, so now you can see that there's a there's a difference, right? None of these numbers are the same now, right? With the reflection, there's one number that stayed the same, but now with this rotation, all the numbers change. Interesting. Okay, so just like we I already erased it. Anyway, just like we multiplied those two guys, I want you to try your hand at this kind of a calculation. So take that rotation and multiply. See what happens when you do it 3 times. Okay, so put 3 copies beside each other. Try that out.
Does that bracket thing mean like we need to do that thing first?
Yes. Or it's helpful to do that first.
Okay.
Awesome.
Yeah, but usually too, when you spin a triangle.
Do you know if there's these partnerships for physics? Okay.
My school? Yes, because we're
It's a pleasure to do this.
our program.
Oh, I asked the stupidest questions. I asked the question of the That's not a good question. That's a question that I like to say exactly what it is.
I think I did it.
Nice. Nice. Good, good, good. Okay, so people tried out the multiplication thing. Give it a shot. Yeah, I got like one thumbs up. Thank you. Thank you, my people. Amazing. So this bracket here, it's just a suggestion that you multiply those first. Okay, so you multiply those guys first, and you get this guy here. Right? So the stuff underlined becomes this this symmetry. Right? So what I find really like nifty about this calculation is I don't know what that second symmetry looks like, but I know that it's right. Neat. Okay, so we do the multiplication. Now we've got two more matrices that we can multiply. And that one, yes.
Can you just do all three together?
Yeah, of course. Yeah, sure. Yeah, you'll wind up with the same thing.
Yeah.
Right, so we go 1 goes to 3, 3 goes to 1. All right, and we do it, we get that everything goes to itself. Okay? Because if we take that triangle, rotate it once, twice, 3 times, we've rotated all 360 degrees. We're back where we started.
So the second matrix, the second, after you multiply, yeah, that one.
Yep.
That one would just be a symmetry of two rotations.
Perfect. Yes, that would be a 240 degree rotation. Yeah, nice. And it's cool that the 120 and the 240 cancel out somehow. Nice. Okay. So the rotation of a triangle performed 3 times cancels out. Great. Okay. So now we're going to go kind of into the algebraic deep end of things. We're going to go and look at not symmetries related to specific shapes now, but just the notion of symmetry in general. So we're just going to look at, what are these matrices really doing? What do they mean? Etc. Okay, so we're gonna abstract away from the triangle. Mathematicians make a lot of progress by taking a specific concrete thing, like that triangle, and then coming up with a formula or a way of understanding it mathematically, and then generalizing away from the triangle. Right? So mathematicians can be inspired by physical objects, then they do algebra, they create systems, and then suddenly they're dealing with a whole other thing that might have applications elsewhere. But in my experience, mathematics always begins with a specific triangle. Okay, so one way is we can just get rid of the triangle. And note that these arrows are really telling us everything that the matrix is telling us. Right? So we know that 1 goes to 3, 3 goes to 2, 2 goes to 1. That's one step more abstract. Okay. Right. What would the picture look like if we went the opposite direction? Where would the arrows be going then? Yes. Yeah, they're going counterclockwise, right? So 1 would go to 2, 2 to 3, 3 to 1. Right? Neat. Okay. So there's a symmetry out of the triangle. What symmetry is this?
To reflect.
Right? This guy. Right? But now we're just talking about where those vertices go. Right? So notice that 1 has an arrow going back to itself. Right? 1 gets sent to itself under this symmetry, and then the 2 and 3 switch. Okay. So we've abstracted away the triangle. We just see these things as functions now. So now, let's start with something mysterious and see if it could be an allowable symmetry under these rules. So I've added in a couple more numbers. And we've got some arrows. So take a moment, stare at that. Really, just stare. Does this look like it could be a symmetry of anything?
No.
What? Oh, yes. Okay. Ooh, interesting. That's. I hear some yeses, some nos. Yes.
Could it not be a reflection?
There's nothing flowing.
Like, if the shape is
Oh, because 4 is fixed.
4 is fixed.
4 is fixed. So if it'd be a reflection about an axis through 4 or something, maybe, yes. But is there anything that seems kind of weird about these arrows? Okay. All right. Oh my gosh, there's so many hands now. Okay, guy in the red shirt back.
There's some numbers going multiple into 1, and some are going multiple into, sorry, they're going into multiple numbers.
Right. Okay. So what's an example of that?
6 is going into 1, 3, and 5 and 3 are going into 2.
Ooh. Okay. That is weird, right? Okay. Any other weirdnesses people noticed? Yes, guy with the hand.
You've got some numbers that have no arrows flowing into it, like 5 and 6.
Yeah. Right. There's just nothing. The symmetry sends nothing to 5. It's like you rotate the object and then that one just goes away, right? That's weird. And with your comment, you know, it's like you apply the symmetry and then 6 splits into 2 things. That's weird. 6 should only go to one specific spot, right? Yes.
I was going to say that because we've approximated the symmetries as functions.
Yep.
And in functions, every value can only go to one other value.
Yes.
And that means that 6, since it's 6 is it's applied to both 1 and 3, it doesn't work.
Right. So this is.
Based on a functional model.
That's really cool. So yes, so this is exactly what mathematicians do. We say, okay, well, we have this way of thinking about things as functions. If symmetries are functions, then every input should have one output, right? But we can't like have a function, right? So we can't have a function that says f of 6 is equal to 1 and 3 at the same time, right? Functions don't do that. Yes?
Aren't there piecewise functions though?
There are piecewise functions, yes. But functions, often we think of them as an algorithm with one output.
Yeah.
Right? So we can say f of 3 is 2, and f of 5 is 2. That's fine. But there's something weird where we output 2 numbers. Right? That'd be like where we've got a graph and then suddenly there's 2 points right above each other. Very weird. Okay. Are there any other weirdnesses people have noticed? Other things? Yes?
Like 1 and 2 both don't have an output, like
Yeah,
they
right?
have an arrow going to other numbers.
Yeah, like if this was a function, we'd you know, put 1 and then f of 1 would have nothing. Right, so very, very strange. And 2, same thing. Okay, so yes, I think we've spotted all the weirdnesses here Things with more than one output, like 6. Things with more than one input, like 1 and 2. And also, as you pointed out, those things don't output anything. 1 and 2 don't output anything, which is very odd. Okay, so if we're going to model symmetries as functions, then we can't have this. Okay, symmetries have exactly 1 in arrow and 1 out arrow per number. Right? We have exactly 1 out arrow because we're a function, and we have exactly 1 in arrow because our symmetry can't squish stuff together. Right? We can't take 2 parts of the triangle and then just glue them. Doesn't seem fair. Right? Thoughts there before we go on? Okay, got this. Okay, so now I'm going to rejig the arrows a little bit, and we get something like this. This seems fine. This could be some kind of a symmetry. Maybe it's a 6-dimensional object, I don't know, but all the rules about 1 in arrow and 1 out arrow are satisfied here. So we represent this as a function. Okay. Oh, right. I forgot what my next slide is. So, what we notice is that the figure splits up into these little collections of loops. Right? So there's a loop from 6 back to 6. There's a loop between 1 and 4, and between 2, 5, and 3. So when we abstract away the particular geometric object, we can start to see patterns that we might not have noticed before. So one is that for these functions with exactly 1 in arrow and 1 out arrow, everything has to decompose into loops. Everything decomposes into cycles. Okay. Is it clear what I mean by that? Got this? Can anyone think of why that should be true?